we doing? How was your extended weekend? Good. Before I forget, at 10:50, a Moodle quiz is going to open up over using exponential models to solve the problem. It's been a little bit since we talked about that, so I kind of wanted to review it before the next test popping up here shortly. Okay. So in Moodle, it'll pop up open, available at 10:50. It'll be due tomorrow night at midnight, 11:09. Okay. All right. So I will also send out an email reminder tomorrow. Make sure you remember that. Okay. There's 5 parts to the problem, but they all relate to the same problem. I just copied and pasted the stem of the problem all the way down for reference. Okay. All right. So let's continue with our discussion of, I should ask, any questions over anything at all? All right. So let's continue on with our discussion of solving systems of equations, 3 variables and 3 unknowns. This is a problem we almost finished at the end of class last Wednesday. So we got to this point where remember again, we're trying to put the system into that triangular form, which helps us read the answers a little bit more quickly. But when we got to the end here, when we got to the x here, we eliminated the x's below it, got the y, eliminated the y's below it. When we got to that point, though, there weren't any z's down here, right? Got to that 0 equals 0. Is 0 equals 0 a true statement or a false statement? It's true, right? So that's telling us we have infinitely many solutions at this point. We want to write them in what's referred to as parametric form. Hope talked a little bit about that when she taught. We'll do it a little bit, the same idea. WebAssign wants you to enter it, I think, a slightly differently, but it's the same kind of concept here. Notice that if I have a value for z, say z were equal to 2, could I solve for y and x easily? If z is equal to 2? Yeah, because I would just plug the 2 in here and move the stuff over to figure out what the y is, right? And then once I have the y and the z, I can do the same thing with the x, correct? Okay. So we do that same type of back substitution. We just don't do it for a single number. We do it for any possible z. So for this one, I would solve for y. I would add the 5/2 z to the other side. And again, if I know a value for z, then I know a value for y, right? So doing that back substitution idea again, here, I would plug in the 5/2 z minus 4 minus 2z equals -1. I took out the y and put in 5/2 z minus 4. Whatever that number happens to be. Okay? And then we can simplify 5/2 minus 2. 2 is the same thing as 4/2. So you'll have x plus 1/2 z minus a 4 equals -1. Or finally, x equals -1/2 z plus 3. So when you write your final answers, my x will be -1/2 z plus 3. Your y will be 5/2 z minus 4. And then just a z on the end because the z can be anything at once. Okay. We refer to this as parametric form. Again, this is just representing that I can pick whatever I want for z. What number I have, I can plug that in. This is what the y value has to be. Again, whatever the z value is here, I can plug that in here, and that tells me what the x value has to be. It's still that back substitution idea. And we'll see more of these as we go along. Okay. Questions? Okay. Let's do the next one here. All right, so the next one, again, we're going to do this with elimination. We've got 3x minus 2y plus 2z equals negative 2. X minus 3y plus z equals negative 2. 2x minus y plus 4z equals 7. I want to try to get that in rectangular form. Remember, we're doing it very, very systematically. 1 in the upper left-hand corner, 1x in the upper left-hand corner, right? Get rid of the x's below it. Go to your second equation, get a 1y, get rid of the y's below it. At that point, you should have, hopefully, just have a z by itself, or a number times z, right? That's the idea. If I want to get a 1 up in that upper left corner, what should I do? Okay, that's one way we could do it. We could divide by 3, right? If I divide by 3, I might introduce some fractions. Is there another way I could get a 1 in the upper 1x up in the upper left-hand corner without dividing? What's something else we could do? What's something else we could do? We had 3 things that we could possibly do to keep equivalent systems. One was to multiply by a constant. What was another one? It's probably the first one I wrote down. Swap them. Yeah. Can I just swap the first 2 equations and get a 1x in the upper left-hand corner? Yeah. Look for that first, right? And that'll hopefully eliminate fractions. Sometimes you can't avoid them, but I'm going to try to avoid them if I can. Okay? So we'll do, remember our notation for that was E1 and the double arrow and E2. So I'll have x minus 3y plus z equals negative 2. 3x minus 2y plus 2z equals negative 2. And the third equation doesn't change. All right, so now we have a 1x up in the upper left-hand corner. What's our next goal? We want to try to get a 1y here, and in order to be able to do that, what do I need to do with this 3x and 2x? We're getting rid of them, right? I got to eliminate them, don't I? Okay. Always work off the thing that you got a 1 here first. Okay. What do I need to multiply this by? So that when I add down, I get 0. Negative 3, right? Do negative 3 times the first equation. Add it to the second equation. Replace the second equation. Does that change the first equation at all? No. Remember, we're just doing that multiplication as an intermediate step. It's the second equation that we're replacing, right? So our first equation stays the same. Let's work on the second equation. Negative 3 times x is negative 3x. Plus 3x gives us 0. It's what we want. Negative 3 times negative 3y is positive 9y. Minus 2y gives us 7y. Negative 3 times z minus 2z. Negative z. Negative 3 times negative 2 is positive 6. Minus 2 gives us positive 4. Let's see if we can do the next one in the same step here. I got rid of this 3x. Are we okay with that second equation? What do we need to do to get rid of the 2x in the third equation? Yeah, multiply by negative 2, that first equation, right? When you're getting zeros below, make sure you're always working off that 1, right? Okay? This is going to be important in the next section too, okay? So we're going to do negative 2 times equation 1. And I'm going to do it in the same step here. Negative 2 times equation 1 plus equation 3, replace equation 3. That's certainly going to give me a 0 here. Negative 2 times negative 3 is positive 6. minus y gives us positive 5y. Negative 2 times 2z, or not times 2z, times the z added down gives us what? Negative 2 times z plus 4z gives us, is that z plus 2z? Because it's minus 2 plus 4? Yep. It's easy to make little arithmetic mistakes here. Negative 2 times negative 2 is positive 4. 4 plus 7 gives us 11. So far, so good? Okay. Like I said, I try to avoid the fractions if I can. Unfortunately, I can't mess with this equation at all because I'm using that as my upper left-hand corner, right? So basically done with that equation. I need to make this a 1y. Well, swapping isn't going to help us very much, is it? All right, so the best thing that we can do here is just divide both sides by 7, multiply by a 7th. So that doesn't change the first row or the first equation. In the second equation, we get y minus 1/7 z equals 4/7, and the third equation stays the same. All right, so again, remember our process. Got a 1x, got a 0. Now we're got a 1y. What's the next thing to do? Yeah, that needs to go away, doesn't it, right? The process is always going to be get a 1, get zeros. Get a 1, get zeros. Get a 1, get zeros. Okay? This will be our process for all of these things. Okay? What do we need to do to make this 5y go away? Good. Negative 5 times the second equation, added to the third equation, replace the third equation. What's the only equation getting changed? The third one. Good. Okay. It made that 5y a 0. Now I've got to do negative 5 times negative 1/7. That's going to be 5/7. Right? 5/7 plus 2. 2 is 14/7. So we get 19 over 7 when I'm done. Negative 5 times 4 over 7. That's the next one, right? Negative 5 times the constant. Negative 5 times 4/7 is negative 27. 11 is 77/7. Negative 20 plus 77 gives us 57/7. I know the fractions are ugly. Is the process okay what we're doing though? I just took the negative 5 times each of these three things and added them to each of those three things. You need to use your calculator for the fractions? Please do. And I can show you how to use your calculator to do fraction computations too if you need to. All right, so let's recap. What have we done? Got a 1, got zeros, got a 1, got a 0. What's the next step? Get a 1, right? We're going to alternate, right? 1, zeros, 1, zeros, 1, 0. It's always going to be alternating. Okay? What do we need to do to turn that 19 over 7 into a 1? Well, what did we do to get rid of the 7 earlier? We divided it, right? We need to divide by 19 sevenths. Dividing by a fraction is the same thing as multiply by the reciprocal. Good. We'll multiply by 7 over 19. And again, at this point, this is only changing the third equation. So the first two equations are staying the same. Multiplying by 7/19 makes the coefficient a 1. What do you get when you take 57 over 7 and multiply by 7 over 19? Actually, it comes out to be nice. The 7s will cancel. 57 divided by 19 is what? You get 3, don't you? Yep, 3. I agree. Yep. Cool. Have we put this in triangular form now? Yeah. What does z have to equal? 3. Good. How do you figure out the y? Good. Plug in 3 for z and solve for y. Well, 3 times 1/7 is 3/7. We'll add the 3/7 to the other side. We'll get y equals 1, it looks like. Now what do we do? Good, plug in the y and the z and figure out the x, right? X minus 3 times 1 plus 3 equals -2. Well, -3 plus 3 just gives you 0 on the left-hand side, doesn't it? So we end up with x equals -2. And then again, writing our answer here as an ordered triple, we'll get x, y, z equals -2, 1, 3. What questions do you have? Say again? How's it 1? Okay. Okay. All right. All right, work on the next one for a minute, and then we'll chat about it. Those are the one on the top. Sorry, I just scrolled a little too far. You want them? In all these problems, what do we want first? Yeah, so 1x in the top left, right? Do we have to do anything to do that in this case? No, it's already set up that way. All right, so we got a 1x in the top left. What's next? What do we want below that 1x? Zeros, right? Get zeros below it. So to make this 3x right here go away, what do we want to do? Good. We'll do -3 times equation 1 plus equation 2, replace equation 2, right? That does not change the first equation. What does the second one become? Okay. minus, I think it's 7z, isn't it? Equals, I'm sorry, 19, is that what you said? Okay, that's what I get. I just want to make sure I heard you correctly. Yep, 19, yep. Cool. Do we see where those numbers came from? Let's go through them by step here. Negative 3 times y is negative 3y plus negative 2z, right? That's where the negative 5y comes from. I don't know why I said a z. Try that again. Negative 3 times a positive y is negative 3y plus negative 2y is negative 5y, right? Negative 3 times z is negative 3z minus 4z is negative 7z. Negative 3 times negative 1 is positive 3 plus 16 gives me 19. What did you get for the third equation? What do we need to do to get rid of this 5x right here? Good. Multiply by negative 5. Equation 1 plus equation 3. Replace equation 3. That makes the 5x go away. What do you get for the y term? Minus 5y. What do we get for the z term? Minus 7z. And what do you get for the constant? 8. Okay. Again, to go through those. Negative 5 times y will give you negative 5y. There aren't any y's down here. So I still get a negative 5y. Negative 5 times z is negative 5z. Minus 2z gives you negative z. Negative 5 times negative 1 is positive 5. Times 3 gives you 8. What do you notice about those two equations now? They're basically the same, aren't they? I've got the same thing on the left-hand side. Do we have the same thing on the right-hand side? No. Right? Let's go through the next step just to make sure we're all on the same page and see what happens. But what do you think is going to work here? Can whatever number negative 5y minus 7z give you, can it be 19 and 8 at the same time? No. So this is going to have what? When you're done. Is it going to have any solutions? No. Let's see why. Again, let's just go through the rest of the process and make sure we understand where we are with this. What's your next step in the process? Get a 1 here, right? What do we need to do to turn that into a 1? Divide by negative 5. That's multiplying by negative a fifth. We don't change the first equation. The second equation becomes y plus 7/5 z equals negative 19/5. And the third equation stays the same. What's next? We got a 1y, so the next thing to get is a 0 below it, right? When I get a 0 below it, what do I need to do to make this a 0? Good. Multiply equation 2 by 5. Add it to equation 3. Replace equation 3. It doesn't change the first two equations. It makes the one right below the y a 0. 5 times 7/5 is 7. Minus 7 gives you 0. 5 times 19/5 is negative 19. Plus 8 gives you negative 11. What can you say about this here? It's false, isn't it? It's a false statement. We got 0 equals something that's not 0. So if it's false, what does that tell you? There's no solution. Good. So this is false. Oops. So no solution. Do you have a question, Claire?
Yeah, why do you multiply by the negative 1/5 for equation 2, but do just regular 5 to be equation 3?
Okay, so I didn't multiply equation 3 by 5, right? I multiplied the second equation by 5 so I could add to that to make it a 0. I'm trying to make this go away, right? So I need to multiply by the opposite of it so that when I add, it makes it go away. Just like we did up here, right? We had a positive 3 here, so I need to multiply by negative 3. Same idea. Yep. Because remember, I'm not trying to turn this into a 1. I want to make it go away. So the answer to this one then is no solution when you're done. What questions do you have? Okay. I'm going to leave the rest for practice. I will post solutions on Moodle for those. But I'll leave it for practice for you. And if you've got questions, of course, feel free to come see me or come see Hope. Either of us are happy to go through those. But I want to flip over to the next topic today, and we'll finish this up on Wednesday, where we're going to start talking about matrices. Okay. So this is the handout that I just got out. I'll give you one. There you go. All right. So when we talk about a matrix, what we mean by a matrix, and you can see some examples already on the page if you look down, but what we mean is that we have some rectangular array of numbers. So that's what we mean by a matrix. So again, you can see an example down at the bottom. This is what we mean by a rectangular array. If you're familiar with Excel, those give you rectangular arrays as well. But notice I've got a couple of rows of things and some columns in here. All right. What we call each number in this array, we refer to that as an entry of the matrix. So every single number in the array is called some entry. Okay. You may notice that on the page, I don't have them both on the screen right now. On the page, I have two different matrices listed there. One, they look different, don't they? They have different size rectangles. When we talk about the size of the matrix, we use the word dimensions. So the dimensions of the matrix. That tells us how many rows and how many columns we have. So in this example that is at the bottom of the screen, how many rows do you see? 2. How many columns do you see? The columns that go the other way. So I got 2 rows. We got 1, 2, 3, 4, 5 columns, right? So the dimensions of that would be 2 rows by 5 columns. The way we write it in general, if m is the number of rows and n is the number of columns, we'll write m. It looks like a times sign. We say m by n is the way we say it. So it's an m by n matrix. M is the number of rows. N is the number of columns. So number of rows comes first. Number of columns comes second. Okay? That's the notation we use. Let's say I want to specify a specific number. Specify a specific number. That's not redundant at all. Okay. Let's say I want to specify a particular number in the array, in the matrix. Okay. We use, typically, notice that in the 2 examples again that I have listed for you on the page, typically we use a capital letter to denote a matrix. A, B, C, M, N. Okay. We use the lowercase letter to accompany it for each entry. So if I want a particular number in the array, we'll use a lowercase entry that corresponds to the uppercase letter we're using to denote the matrix. And then we use subscripts. Usually we write an I and a J. The first number is the row. The second number is the column. Okay. Your first number in the subscript is the row number. The second number is the column number. We typically just put them side by side. You're not going to have matrices that have more than 9 rows or 9 columns. Okay. If you had something that had like 10 or 11 rows or columns, you'd put a comma between them. But typically we don't put the comma in there. Okay. All right. So let's look at this example. You just told me a minute ago A has how many rows and how many columns? Other way around. Yeah, 2 rows, 5 columns, right? So we would say that A is a 2 by 5 matrix. Okay. Again, the 2 refers to the number of rows. The 5 refers to the number of columns. So it's a 2 by 5 matrix. Okay. If I asked you, what is A sub 1 4? Won't be a negative 1. I think you went over too far. Yeah, it's the 4th column, right? So it's row 1, column 4. So I'm looking at that number there. It's a 2. If I want A sub 2 3, that'd be the 5. That'd be this one here. Good. Sometimes they like to be tricky. If I ask you for A sub 3 1, what row does that tell you to look for? The 3rd, are there 3 rows? No, so this is just undefined. Every once in a while they try to be tricky. I think it's pretty stupid, but every once in a while they'll try to do that. Okay. All right, does that make sense? Okay. All right, let's look at the next one. Dimensions of B. 4 by 3, good. So dimensions 4 by 3, right? Number of rows by number of columns. Or you could say B is a 4 by 3 matrix. Those all say the same thing. So if I ask you about some numbers in particular, if I want little b sub 2, 2, you would tell me it is negative 3. Because again, we're looking at row 2, column 2, that one right there. If I asked you for b sub 3, 3, negative 8. If I do b sub 4, 1, I'll get 1. B sub 2, 3. Negative 2. Good. Everybody seeing where those are coming from? That's not too bad. Okay. All right. So that's just giving you some introduction into matrix notation, some matrix definitions. For at least to start with, our main goal for using matrices right now is as a bookkeeping idea. We're going to use matrices basically to keep track of numbers to help us solve systems of equations. That's our first goal of these things. Okay? So to do that, we're going to create from a system of equations, we're going to create something that's called an augmented matrix. And let's talk about how that works. Okay? How many equations, in this first example, how many equations do you see? 2 and 2 variables, right? Okay. Good, there we go. All right, so I see two equations and 2 variables. So each equation is going to correspond to a row, and each column is going to correspond to a variable. So the way we typically do it is our first column will refer to the x's, the second column will refer to the y's, and then we'll have an extra column for the constants on the other side. Okay? All right. So the way we're going to write this And I'm going to label the columns to start with, but you don't have to label the columns every time. So the first column here is going to be your X column. Your second column will be your Y column. Your third column here will be your constant column. Okay? And we're going to just write the coefficients in that order across, not worrying about the X's or the Y's. Okay? So the first entry here will be a 3 for the X. That's the coefficient on the X. The coefficient on the Y is a -1, because I've got a minus sign there. The constant is 5. What's the second row going to be, do you think? 1, 4, -2. Good. Now, here's where the augmented part comes in. I have equals here, right? My X and my Y are on the opposite side of the equation as my constant. So we're going to put a vertical bar in there to denote that equal sign, okay? So part of this is going to be able to go back and forth, right? Take our system of equations, write it as an augmented matrix, and then vice versa. Have an augmented matrix and write it as a system of equations. Okay? That's our goals here. All right. Now, notice that this was nice and set up for us, right? I've got my X's stacked, my Y's stacked, my constants stacked on the other side of the equation. Do I have that here in the next one? Okay. Before you create your augmented matrix, it has to be in that nice standard form, okay? So in the first equation, my first equation, I need to subtract that 6y over to the left, and I need to add the 7 to the right. I want all my variables on one side, all my constants on the others before I do an augmented matrix. Okay? I need to do the same thing for the other equation, but notice it's got an over 5 in there, right? So the first thing I need to do, well, you could multiply both sides by 5, I suppose. Doesn't really matter. But actually, I'm going to do that. I'll do this over to the side here. If I multiply both sides by 5, I would have -15y equals x minus 2. And then again, I need to have everything on one side for my variables. So I would have -x minus 15y equals -2. Now I have my x's stacked, my y's stacked, and my constants stacked with the equals there next to the constants. So what's your first row going to be? 3, -6, 7. And the second row will be? Good. Everybody see where that's coming from? Okay. So far, we've done it for 2x2 systems, right? 2 equations and 2 unknowns. We can also do it for 3 equations and 3 unknowns. Again, just making sure we have everything stacked. In the first row, what do you think we're going to write across the? Yes, Maya.
For the answer, you have to have brackets.
Yes, the brackets are because it's denoting a matrix, so we'll put the brackets on the edge.
Okay. And then you have to put exclusive brackets.
For the system, usually we do just to note that we're trying to solve the equations at the same time. Yep. Yep. What's your first row look like, do you think?
1, -1, 2, 4.
Good. And notice the 4 is going to go on the other side of the vertical bar because, again, the vertical bar is representing where the equal signs would be. How about your next row? Good, fantastic. There isn't a z in that second equation, is there? So the coefficient on it would be a 0. So we'll have a 1x plus 7y plus 0z equals -1. What about your third row?
0, 1, 8, 9.
Good. That okay? All right. Let's see if you can go the other way. I give you an augmented matrix and ask you to write the system. Okay. 2x plus 5. 5. There we go. There we go. Equals -1. Yep. Okay. Again, we're not really told what the variables are, but everything we've done has been, for 2 variables has been x and y. For 3 variables has been x, y, z. So as long as you're consistent with your variables, it doesn't really matter what you name them. Okay. Everybody okay with where those came from? How about the next one? Okay.
X plus 7z equals -2. And -3y minus 2z equals 1.
Good. Making sure you're keeping track of where those zeros are, right? In that first row, we have a 0z. In the second row, we've got a 0y. In the third row, we've got a 0x. That okay? All right. So one of the things that hopefully you've noticed going through the problems when we've been doing elimination in particular is that the x's and the y's and the z's haven't really mattered. We've been playing with the coefficients, right? So really what we're going to be doing is just using these matrices as kind of record keeping to try to keep track of the coefficients and then go back and get our solutions at the end. All right. Hopefully, and again, we talked about doing getting in triangular form. The form that we're going to talk about for the matrix here in a second is the idea of this triangular form idea. And we're going to refer to that as reduced row echelon form. Basically, when we do reduced row echelon form, we're talking about a special triangular form. And that special triangular form allows us to read the answers off more quickly. Okay? So what do we mean by it being in reduced row echelon form? Well, the first part is that all rows of zeros, if there are any, are at the bottom of the matrix. Okay? If you have a row that's entirely of zeros, it has to be at the bottom. Okay? For any non-zero row, the first non-zero entry of a row must be a 1. If it's a non-zero row, the first non-zero entry must be a 1. Now let me just write it this way. As you move down the rows, we refer to those, by the way, I should mention this. We refer to these as leading ones. Or pivots. Those are names that we give those. As you move down your rows, the leading ones move to the right. They stair step, basically, right? And that's that triangular idea, isn't it? That we talked about. We got a 1 for the x's, and then we got a 1 for the y's, and then we got a 1 for the z's. And we got zeros below it as we went. Okay? That's the idea. The last thing, to put it in reduced row echelon form, is that, stop it, every entry above and below a leading 1 must be a 0. It has to have zeros above and below it. Okay? This is what puts a matrix in reduced row echelon form. Okay? So let's look at this one example. We'll do more of this next time, but let's look at this one example before we go. Okay? Are there any rows of zeros in this first example? No. Okay, so all the rows of zeros are at the bottom because there aren't any. Okay. Is the first non-zero entry in any row a 1 as you read across? Is that a 1? Yep. Is that a 1? Oops, I'm sorry, I pointed the wrong thing. Is that a 1? Yes. Is that a 1? Yes. Okay. So we have first entry is a 1. Okay. Do we stair step to the right, down and to the right as we go? Yep. Okay, that's part 3. Is every entry above or below these leading ones a 0? Yeah. So this is in reduced row echelon form. Why do we like it? Can you read the answer? What's the first equation say? The first row say? X equals 4. Second row says y equals -3. Last one says z equals 1. This is why we like reduced row echelon form. So what we'll talk about on Wednesday is how to put matrices in reduced row echelon form. Okay? Don't forget, quiz over exponential models on Moodle, due by midnight tomorrow. Well, 11:59 tomorrow. Okay. Have a good one.